All right, this technique is going to be immensely helpful when we talk about the graphs of functions, particularly when we bring up what a derivative is and higher order derivatives. We're interested in whether or not functions are positive or negative. So take a moment now, pause the video if you have to, go back and review what the intermediate value theorem told us. Right? Because as a consequence of the intermediate value theorem, we obtain kind of like a corollary. The only way for a function to pass from down here to up here, right, from negative values to positive values, is to either pass through your x-axis and give yourself a 0, or it can experience a discontinuity, right? It can jump, or it can have a removable discontinuity, right? But the only way for a function to change sign from negative to positive is to either pass through the x-axis or to jump over the x-axis and experience a discontinuity. So if we're constructing sign charts, the only place a function can change sign is at these points, zeros or discontinuities. So that's what we need to look for. This function here, p of x, is a rational function. It is cubic divided by a square. So let's look at the zeros first. What's going to make this function, p of x, return a 0? Well, I've got a fraction equaling 0. Right, so what's going to make the factors in my numerator 0? X is equal to 0, x is equal to -1, x is equal to -7. These are all places where I need to check my function. So -7, -1, and 0. Let's look at the discontinuities. So what's going to make p of x not exist? So I've got a polynomial divided by another polynomial. They both exist independently always. The only problem is I might divide by 0. So what's going to make x squared minus 4x equal to 0? Right? Because if I divide by 0, then my function doesn't exist. I've got a discontinuity there. It might be removable or non-removable. So when we solve this, we factor that x out. You get x minus 4 is equal to 0. So the two places are at 0 and positive 4. So in fact, you do see that x is equal to 0 is a removable discontinuity. It was a 0 of your numerator and it was a 0 of your denominator. But that's neither here nor there. We're going to construct a chart, and the only possible place where this function can change sign is at the x value -7, at the x value -1, at 0, or at 4. Okay, so if these are the only possible places my function can change sign, if I'm positive over here, that means I'm positive over that entire interval. So effectively, I can just take test points and figure out if I'm positive or negative. And if I'm positive the entire way. If I'm negative the entire way. So let's look at a few test points. Let's look at something on the left side of -7. Let's say -10. Something in between -7 and -1. Let's say -2. Something in between -1 and 0. Let's say -1.5. Something in between 0 and 4. Let's choose 1. And something greater than 4. Let's choose 5. Right? Nothing special about these points. Just some test value inside each of these intervals. So let's see what's going on with our function. If you plug in -10 into your function there, you're going to get -10 plus 7, a -10 plus 1, a -10 over a -10 squared minus 4 times -10. In fact, I don't really care about what value this is. I just care if it's positive or negative. So let's go back to its factored form. Let me get rid of some work here. This function, we can simplify it as x plus 7, x plus 1, x over x minus 4. Those x's can cancel. X plus 7, x plus 1 over x minus 4. So now when I think about plugging in minus 10 into this, a minus 10 into that factor right there is going to give me a negative value. A minus 10 into this factor is going to give me a negative value. And a minus 10 into the denominator is going to give me a negative value. So the negative times the negative in the top gives me a positive. If I divide that by a negative, that gives me a negative number. The function value is negative here. So it's below the x-axis. Right? So if the function value is negative there at minus 10, it's negative on the entire interval minus infinity up to minus 7. Let's do the same thing for all of our test points. So if you plug in minus 2, let me go back to the simplified version. If you plug in minus 2, let's think about the factors. First factor is positive. Second factor in the numerator is negative. And the factor in the bottom is negative. So negative, negative gives me a positive. The function is positive there. The test value of minus 1/2. So that first factor is going to be positive. Minus 1/2 plus 1 is positive. Minus 1/2 minus 4 is negative. So in total, I get a negative answer right there. When I plug in a 1, I get a positive times a positive over a negative. I get a negative answer there as well. And if I plug in 5, what am I going to get? A 5 in the first factor is going to give me a positive. 5 plus 1 is a positive number. And 5 minus 4 is, again, another positive number. So everything over there is positive. My answer is positive there. So I can actually give myself a pretty decent idea of what the graph is going to look like. I'm negative until I hit minus 7. I'm then positive between minus 7 and minus 1. I'm then negative on the right side of minus 1, though. Right? I'm negative between minus 1 and 0. In fact, I'm even negative on the other side of 0. So just because you could have switched sign from positive to negative or negative to positive at 0 doesn't mean you actually have to. So I'm still negative, although I don't exist at 0. So maybe we have an open circle right there, and you're still negative. And then you're negative all the way until you hit 4. And then on the right side of 4, your function's positive again. Ooh, I forgot my asymptote. Where was the asymptote? Actually, the asymptote was at 4. So if there's 4, and you switch to being positive on the other side of that asymptote, and you're positive on the other side of that as well.